Hi, this is Rob Bolaños. Welcome to how to measure the loop response of a power supply. In this video, I'm going to go ahead and measure the loop response, and one of the reasons that we do that is to verify the stability of your power supply. So that's one of the biggest thing, that if you don't design it specifically your compensation, then you're going to have instability. You might have oscillations. Okay, so, and if you measure the loop response, then you can verify that you're not going to have any conditions where it's going to oscillate. Okay, so I'm going to be also showing how to use the Bode 100, which is a frequency response analyzer, and I'm going to measure the transfer function of the output filter. Okay, so the output filter is actually a low pass filter, kind of looks like this, and then it's got a pole, and then it's got a zero. So when we measure it, we extract the pole, and then we can extract also the zero as well. And once you have that, then you can do a spice model, and you can measure and compare it with your spice model, basically verify it. And if there's a little bit of discrepancy, you can adjust the spice model to match your measurement. Then we're also going to go ahead and measure the transfer function of the error amp, and we should get something like this. We'll have a integrator function, and then it breaks to a horizontal, and then it breaks down like that. So by measuring, okay, at low frequency, you're going to get a Z, which is a 0, and then at a higher frequency where it starts breaking down, that's your pole. Okay, so by measuring it with the Bode 100, we were able to see these two transfer function. And as well, once you have a measurement, then you can compare it with your spice model and verify that your spice model is working correctly. Once we have those two, then we can take the total loop, which is this one, which is basically a combination of all the transfer functions that go around the loop. And to have a stable power supply, the absolute minimum phase margin is 45. That's the absolute minimum. Uh, there's other power supply designers that may go up to 60 degrees of phase margin. That's what I try to design, typically for 60 degrees. I prefer that. And then your gain margin greater than 10 dBs or negative 10 dBs. So if you have greater than, you write it out, greater than, then you should be fine. Okay, so these are the requirements as far as specification is concerned. Got to meet at least 45 at the bare minimum, and negative 10 dBs minimum for your gain margin. Okay, now before we measure, we're going to go ahead and review Bode plots of the output filter and the error amp. Okay. Okay. And here are my assumptions. In this case, I've designed a flyback, and the flyback are the most popular and also the simplest to design type of switch mode power supply. And I'm using discontinuous mode, and the reason that I'm using the discontinuous mode is it simplifies the design by not having subharmonic oscillations. And if you don't have the subharmonics oscillation, it means you don't have to add a slope compensation. And because it's operating in discontinuous mode, you also don't have the right hand plane 0. Okay. Now, if it was a continuous mode, then you would have these two problems. Okay. If you decided to design a CCM, continuous conductor mode, but because I'm using discontinuous, we don't have this problem. Now I'm going to be using a model that was taught to me by my mentor, Jack Alexander. And this makes compensation very, very easy using Jack's model, and also being that it's a discontinuous mode. Now, I will be using approximate formulas, but if you would like to use the exact formulas, I would refer you to the Sanyaya Manitala book, which is a very good book. Another book that I would recommend would be the Steve Sadler Switch Mode Power Supply Simulation with Spice, which is another good book, and I would recommend those. Okay, here we have the output filter. Here we have the load capacitor, and then we have the ESR associated with the load capacitor, and then we have our load. And typically this output filter will have this type of transfer function. Basically, this is a low pass filter. Okay, and right here is your low frequency response. Basically, it's going to be flat, and it continues to be flat until you come to this point, which is your downward deflection. So that downward deflection indicates that you have a pole. And here's the formula to calculate your pole. And then you have this downward slope, and this slope is a first order, and it will have a slope of 20 dBs. Okay, and then you have another inflection or deflection. Now it's going up, and this would indicate that you have a 0. And here's the formula to calculate the 0 of your output filter. Okay, here I'm showing, and in my simulation I'm using a type 2 compensation, and I have my error app. Here I have my integrator resistor, and I have my integrator capacitor, and then I have a roll-off which is connected across the integrator resistor and cap. And then here is my sampling resistors. Okay. Now you can simplify this circuit. You can actually do this. This is another way of simplifying it. You can use this method as well. Okay, so here we have the, right here in red, this is the transfer function of the error amp circuit. And if you notice, at low frequency, you have high gain. And the reason is because at low frequency the dominant impedance between the integrator resistor and the integrator cap, the dominant is going to be the integrator cap. Okay, so at that, it's basically the X of C of the integrator divided by your R Thevenin. Okay, so if this is big, you have high gain. But then as the frequency goes up in frequency, X of Cn gets smaller, so the gain starts to drop. And it drops until the integrator resistor takes over. And at that, you have a deflection upward. It goes up. And when it goes up, then you have a zero. And here's the formula to calculate the position of that zero. And then at here, you have the midpoint, or the midband. And that gain can be calculated by this formula, which is basically the integrator resistor divided by the integrator Thevenin, the Thevenin resistance. And it remains flat until you come to this downward deflection. And when you have that, you have a pole. And here is the formula to calculate that pole. Okay. And if you notice, the slope at this interval is -20, and the slope here is also -20. Okay, so here we're going to put everything together, and here I show my output filter, and then I show my sampling resistors, and then I show my error amp, okay, and then to complete the loop, what I'm using is I'm using a voltage control current source. That is Jack's Alexander model. That's the model that my mentor taught me many years ago. Now, this model is a first order model, okay, and it does have limitations. It does not predict the subharmonic oscillations or the complex poles, so there's limitations, but it is good enough to give you a fairly accurate assessment of the loop. Okay, this method was used in over 100 space qualified supplies that are flying in space that Jack used using this simple method. So it's a method that I feel very comfortable and I've been using for years, ever since it was taught to me by Jack. Now I'm going to be using Jack's Alexander's method of compensating the loop, and again, this is assuming discontinuous mode and current mode flyback. Okay, so the basic idea is of using pole and zero cancellation. What does that mean? Well, what we're going to do is we set the error amps 0 equal to the output filter's pole, and the error amps pole equal to the output filter's 0. And the reason we do this is to cancel them, basically. Cancel. Okay, we're going to line them up. Another way of looking at this is, at least to simplify things, is to use the time constant of the poles or the zeros. So basically, if we use the time constant of the output filter, that would be C load and R load. and we make them equal to the time constant of the error amp, which is the C integrator and the R integrator. So if we set them equal, then you have this equation. And then if we select the integrator and then we solve for the integrator, you end up with this equation. Okay. Likewise, if we set the time constant of the filter 0, we set it equal to the time constant of the error amp's pole, then likewise we get this equation, and if we solve for the roll-off, we get that equation. So basically, you just need to solve for your integrator and your roll-off, and you're pretty much set done. So what does this do, basically? Okay, so this is what graphically what we're doing. So here, this is the output filter. We have a pole. Well, if we use the same time constant, then the 0 will be lined up at the same frequency or at the same basically time constant. So we'll set a 0 here. And by doing this cancellation, what happens is when you multiply the output filter transfer function with the error transfer function, all you have to do is add the slopes. So in this case, this green is the loop. So if you notice, going back to the output filter, this is 0 dB, that's the slope, and you add to -20, then the result is -20. So this is for the first interval, and then we do the same for the second and then for the third. So now we go to the output filter. The output has a -20 dB, and you add it to 0 dB, and the result is -20 dB for the loop. Likewise, we go to the third. Now we have 0 dB, and we add it to the -20 dB of your error amp, and you end up with -20 dB. So this is what you want. You want a straight line where the poles cancel. Okay, so this is Jack's method of basically pole and 0 cancellation. So it makes the setting of the loop fairly easy. Okay, the equipment that we need to measure the loop response is in my case, I'm using the Omnicron Labs Bode 100, which is a frequency response analyzer, and it's also a vector network analyzer. And I will be using an injection transformer. I'll be using the Picotest 2101A. So those are the two measurement of pieces of tools that I'll be using. So this is the way you hook up your Bode 100 to measure the transfer function of the output filter. So the output will be connected through the J2101 injection transformer. That injection transformer will be connected across R6. R6 is a injection resistor, and the top side, I'll call this the top side, I'm going to call it the high side of the injection resistor, and this the low side. Those are the two main test points. Now to measure the output filter, what we want to do is we want to measure the transfer function of your output filter. So what we want to do is we're going to connect channel 2, this here channel 2, and we're going to connect it to the high side of the resistor right there. And then channel 1, we're going to connect it to the COM pin. of the PWM. So this is channel 2, channel 1. We're going to connect it right there. And this is the comp pin of the PWM. And once you connect it, then you should get a waveform looking like that. Here you can clearly see the pole, and you can see the 0 here. Now this is the way you connect to this is the way you connect the Bode 100 to measure the error ramp transfer function. Again, we're using the same injection transformer, and again, this is the high side, low side of the injection resistor, and channel 2 right there, we're going to connect it to, again, the comp pin of the PWM. Channel 2 goes there, and then channel 1 will go to the low side of the injection resistor. So it would go there, and once you have it connected, then you should be able to get a waveform that looks very similar to this. Here you can see the 0. Here you can see the pole. And now that we've done that, now we're ready to measure the output of the loop response. And to connect that, we connect channel 2 to the high side of the injection resistor. All right. And then channel 1 will go to the low side. Once we have the Bode 100 connected across the injection resistor, then we should get a response similar to this here. Here you can see that the crossover is close to 2 kilohertz, and then where it crosses the 0 dB, this would be your phase margin. And where the phase crosses the 0, I'm going to extrapolate that, the difference of where it crosses, the delta, that's your gain margin. Okay, so as long as the gain margin is greater than 10 dBm and the phase margin is greater than 45, you should be fine. Okay, so now we're going to do simulation of the SPICE model, and then we're going to measure and compare both measurements. Here we have the SPICE model. It's an average model, and on top SPICE you can label nodes, and what I have done here, I've labeled this node as CH2, which is channel 2, and this channel 1. And just like in the real Bode 100, you can change these nodes. Now, to take a Bode plot of the input filter, you would need channel 2 at the output, which is this is the output, and then bring channel 1 to the comp pin, which is right here. That would be the comp pin of the PWM. So once you have channel 2, channel 1, you press run, and there you have your Bode plot of the output filter. Okay. So now let's take the Bode plot of the error ramp. So we bring this back, channel 1 to the bottom side of the injection resistor, and then the channel 2 will bring it up to the comp pin, which is right there, So then we can go ahead and press run, and here we have the plot of the error amp. Okay, so now we can bring the channel 2, bring it up to the high side of the injection. So now we should do a complete total loop, and there you have it. So this is the way you do your Bode plots of your output filter, error amp, and then your total loop response. Okay, here I have the uh, pulsar, and I have a small flyback, and I've added test points. Here is one of the test points. This is the red. That's the high side of the injection resistor, and then this black test point is the low side of the injection resistor, and then this blue is the comp pin of the PWM. So those are the three connections that we need. So the transformer goes connected across those two pins. So I'll connect that. Like so. And then if you notice, the Bode 100, the output is connected to the J2101A injection transformer, and then it's connected to the injection resistors. And then channel 1 will be the yellow, and channel 2 will be the green. Now to measure the transfer function of the output filter, we go ahead and connect the green, which is channel 2, to the high side of the injection transformer, and then the channel 1 I connect to the comp pin, which is right there. Channel 1 will go to the comp pin. In this configuration, I should be able to get the Bode plot of the output filter. Okay, so now to measure the transfer function of the error amp, channel 1 will go connected to the low side of the injection resistor, and then channel 2, which is the green, then is connected to the comp pin of the PWM. So in this configuration, we should be able to measure the error amp transfer function. Okay. Now to measure the loop response of the power supply, then we get channel 2, which is the green, then I can connect to the high side of the injection resistor, and then channel 1 I connect to the low side of the injection resistor, and I should be able to plot the loop response of the power supply. Okay, here we're at the Bode Analyzer Suite. We go to the tab that says Vector Network Analysis, and we do a voltage phase gain measurement. We do the start. And before we take a measurement, what we do is we try to calibrate the Bode 100. And what we do is we connect channel 1 and channel 2 to the output of the Bode 100, basically across the stimulus of the Bode 100. And we do a cal. So we go to full range. Okay, and it tells you here, connect channel 1, channel 2 inputs directly to the Bode 100, so they're connected. So press start. Okay, it says it's overloaded. So I lower the input source, let's say to negative 20 dBm. Okay. Do another full range. Okay, it accepted it. So now what we can do is we can do a continuous sweep. And if you notice this, the red is the gain or the magnitude, and it should be flat across the entire frequency range. And then the blue is right here. That's at 0 dB. That would be flat as well. So we can rescale this, make it so. Okay, so once we have this, we can press stop, and then we can make our connections like I showed before. And the first measurement that I'll be taking is of the output filter. So channel 2 will be on the high side of the injection, and channel 1 would be on the comp pin of the PWM. And since the gain is going to be around 5, I'm going to go ahead and lower this to actually 40 right there. And then I'll do a sweep. And before I do that, okay, I have that. Okay, I have a little bit too much signal. So I can go another 25. I'll put it in continuous mode. And you can see the pole right here. And you can see the 0 here. So if we change this to 5, maybe able to see it a little bit better. Okay. So the gain is around 5 dBs. And then you can see the downward, that's the pole. So it's at about 20 to 30 hertz. And then if you notice, you have the 0 starting at about 20, 30 to 40 kilohertz. Okay. Now, there's a little bit of noise here. What you can do is we can put it under variable and then wave. And what we can do is we can double click here, and then we can double click here. That's point, and what we can do is we increase the input stimulus. So now we'll see if this cleans up. And if it doesn't, then what we can do is we can decrease the receiver bandwidth. So it did clean it up a little bit. So then we can go to, let's say, 30. So most of the information that we're looking for is already known. So we know that there's a 0 at about 20 to 30 hertz. And then the 0 is coming in at about 30 to 40 kilohertz. Let's see, cleaned it up a little bit. Yeah. Okay, so that's good. Okay, so then the next is we're going to do the error amp. And we'll go ahead and stop there. So now for the error amp, channel 1 will be on the low side of the injection resistor, and then channel 2 will be on the comp side of the PWM. So in this case, I'm going to have some gain. So I can go ahead and change this value, and we'll put in continuous. So we should have high gain, and then it should start reducing. Okay, so now we're at the mid band right here, and then it should start breaking. So here's a pole. That looks pretty good. So now we have a little bit of noise here at the lower frequency. And mind you, the injection transformer that I'm using only goes down to 10 hertz. So might be able to squeeze a little bit more information if I can change the shape of the signal. So I'm looking at the noise. It looks like it's at 100. So I put a point at 100, and then I'll go to approximately 5 and bring that voltage, let's say, up to 0. See if that cleans it up. It looks like it's cleaning it up a little bit. Okay, so let's see if we can add a little bit more signal. If you might overdrive it. Okay, you can see that there's a inflection up here. So it's around 20 to 30. That's where the zero of the error app is happening. And then the pole is happening about a little bit past 20 to 30 hertz, kilohertz. Okay. So I did clean it up a little bit. See if I can maybe add another point here, and maybe squeeze this up a little bit more. See if that helps. Looks like it helped a little bit. And then what we can do is, okay, go back to the 10. Okay, so if the bandwidth of the injection transformer was a little bit lower, I could confident that I can get a little bit better uh, fidelity down here. But you can tell that the zero happens around 2 to 30 hertz, and then the pole happens at about 20 to 30 kilohertz. So that's pretty much in agreement with the model as well. Okay, so now we're going to do the total loop. Now we're going to connect channel 2 to the high side of the resistor, channel 1 to the low side of the resistor. Okay, so now we should have a nice straight line. Now if it's not straight, we probably have too much signal or we're overdriving. So far it looks pretty good. It looks good. That looks good to me. Okay, so here is the overall, and you can tell right here, this is, you can take the cursor, let's see if I can, should be able to put the cursor, and it's close to 2 kilohertz, it's 1.8 kilohertz, that's the crossover. So we have approximately 75 degrees of phase margin. Okay, and then we can come here, set this where the phase goes to 0. So where the phase goes to 0, we have approximately 37 dBs, negative 37 dB of gain margin. So this looks like a very well behaved power supply. So that's the way you hook up the Bode and set up the Bode analyzer suite. Okay, now that we've gotten the SPICE simulation and the measurements from the power supply using the Bode 100, here you can see the response of the error amp, and if you can see, they look very similar. They're basically almost in agreement. And then we can look at the output filter simulation and the measurement. Again, it looks similar. There's a little bit of disagreement at the higher frequencies, but that's, as long as we're past the crossover frequency, that should be fine. And then we have the simulation of the loop response, which is, if you notice right here, it's crossing at about 2 kilohertz, and it's about 75 degrees phase margin. Here it's close to 2 kilohertz, again about 75 degrees. And here you have a gain margin, let's say about 40 dB. Here it's a little bit off, but I'm okay with this because it's a simulation. I have a measurement. The measurement backs my assessment that the power supply is stable. So this is the way you measure, and you get both simulation and measurement. And with these two coming very close to an agreement, then you can have confidence that your power supply is going to be stable. If you have any questions, you can email them to my YouTube or AOL address. If you find this video informative, please give me a thumbs up, share, and subscribe. And thank you for watching.